Hi everyone, I hope you're doing well these days. My name is Oleg and I'll present our work on the absence of comprehensive edge datasets. This work was done jointly with Gala, Sumit, and Emina. As a fresh PhD student, a few months ago I started researching edge systems and specifically storage on the edge. I've identified unsolved problems and started thinking about potential solutions. Several models were developed to tackle these problems, but then I've reached a dead end. I've realized that I don't have a reliable method to assess all the aspects related to a real edge system due to the scarcity of edge systems and related data. I understood that I was missing something very important, a real edge workload. Edge systems behave differently than traditional datasets. Edge is a local service which is susceptible to fluctuations. It's also a distributed service which is comprised of multiple providers with considerable heterogeneity, which means that optimization is not trivial. So why do we need workloads? Workloads are important for system research, design, and optimization. We use them to define system design objectives, identify optimization goals, make appropriate trade-offs, evaluate, and compare. Workloads can be of different types: I/O requests, CPU, memory, and more. Examples include data access frequencies, which are used for storage caching, job sizes, which are used for resource allocation, and job arrival times, which are used for scheduling. Workloads are further used in benchmarks to evaluate the systems with respect to alternative designs. In this presentation, I will guide you through the path we're proposing for mitigating this problem. I will use the use case of designing and evaluating an edge-based storage system. I will show you how we've managed to generate a representative workload using a composition of multiple datasets. Existing data center workloads rarely reflect the edge infrastructure and its application requirements. In existing edge papers, some of the aspects are irrelevant and thus trivial. Others can be modeled by general datasets which don't affect the purpose of the paper. Some examples include application papers in which many generic datasets can be used, such as any image or video dataset. Security and privacy papers in which the system itself and the data don't play a role. Mobility papers in which any geolocation dataset can be used or even generated by the researchers. And infrastructure papers which sometimes even use trivial system and synthetic workloads. In our use case, which is focused on storage on the edge, key aspects aren't trivial. Also, we can't simply use cloud or synthetic workloads. However, there is no operational edge system that can provide the desired workload. The reason is that there is only a small number of real edge systems which are deployed, and their data is not public. In order to tackle this problem, we start by categorizing the datasets into different attributes: storage metadata, resources for compute jobs, user or application that generated the request, the location it derives from, the system's architecture, and the availability of its components. In our use case, we're addressing storage. A suitable workload will contain I/O requests to an edge service. Each entry should contain a request with information on data object, time, location, and node. These are represented by the marked categories. However, as you can see, the available datasets contain only partial representation of the desired workloads. Storage workloads, which are used for caching, for example, don't contain location attributes and only limited information on user and application. Mobility workloads contain geolocation information and sometimes information on the architecture and users, but information on the objects is missing. Cluster workloads released by large companies contain information on jobs, dependencies, resource utilization, machines, and sometimes on the users. The geolocation information which is relevant to the edge is missing. So how do we bridge this gap? In order to do so, we will join attributes from several available datasets. In our example use case, in which we're interested in an edge-based storage service workload, first we take the NYC yellow taxi trip dataset. It contains information on taxi trips, including pickup and drop-off location and time, number of passengers, fares, and more. However, the locations are represented by New York City zone numbers. We use an additional dataset that maps NYC taxi zones to physical locations. Next, we'll take the NYC hotspots dataset, which contains information on the public hotspots in the city of New York, and we map each hotspot to the zone in which it resides. In our use case, the taxi drop-offs represent the demand in a zone. We will define a browsing session at the drop-off time and zone, and we select a random node from the same zone. For the desired workload, we have generated 3 of the 4 attributes, but the data objects are still missing. We complete the last attribute using Wikipedia dataset, which contains all Wikipedia articles and their links. The browsing session starts at page 0. At a probability of p exit, the session ends, and at a probability of 1 minus p exit, the session continues, moving to a related page 1, and so on. We managed to construct a workload for a session of n pages, starting at time t, at location j, for a node h. Now the picture is complete. This workload can be used to design and evaluate an edge-based storage system. You might wonder whether the composition is a natural one and not a brute force merge of datasets, and whether the combination of the datasets is representative of potential systems. Now I'll show you why we claim it's meaningful. In this graph, the y-axis represents the number of drop-offs in a zone for a period of 3 months. The x-axis represents the number of hotspots in a zone. The black X's mark the daytime rides, the green dots mark the nighttime rides, and the lines in the matching colors are their trends. The red line is the total trend. It can be observed that the demand is changing between different times and different places. We can also see that the two datasets are lightly correlated, showing there is reasoning behind the composition. Additional characterizations we show in the paper include an analysis of objects requests in the Wikipedia dataset, where changing exit rates result in changing object distributions. Analysis of rides in New York City shows non-uniform distribution and mostly asymmetric behavior. Resource allocation and reservation in networked environments use similar characterizations. These are all aspects an edge storage system has to handle and optimize. For our use case, I've shown one set of datasets which can compose a workload. Obviously, there is more than one possible set. Next, I'll show you some generalization examples for our use case. We discuss this in detail in the paper. We can make our workload richer by using datasets with finer location granularity and by incorporating additional datasets. Also, we are not constrained to the datasets we've used. There are many alternatives with which a similar purpose dataset can be composed. For example, we could use the subway dataset instead of taxis and other object request datasets. The lack of suitable workloads is relevant for any infrastructure level design and optimization, not just for storage. For example, task scheduling and forwarding, distributed computation and data processing, application acceleration, etc. Even though these examples address our use case, their concept can be applied to any type of workload composition. To conclude, the use case I presented is only one example of many research topics that need a meaningful workload. This is a general problem. We've described the important categories of dataset attributes, and we've shown how partial datasets can be used to create a meaningful workload. This was our approach to compensate on the lack of edge workloads, but I'd like to hear what you think of it. This approach was developed due to the absence of edge-focused datasets. Obviously, when such datasets will be available, we won't need workload composition. However, is the absence of datasets really temporary? Can we expect companies to release complete datasets that contain information on users, geolocations, architecture, and other aspects? These aspects might be considered to be private or trade secrets. We've shown how a selected set of basic datasets is composed into one workload, but it doesn't mean that it's the best combination. Which basic dataset do you think are most likely to represent future edge workloads? Synthetic distributions can be used to cover large ranges of system behavior, and they are simple to use. How do you think synthetic distributions can be leveraged in our approach? And finally, we've composed our example workload based on our view of how an edge workload should behave. But due to the scarcity of edge systems, it might not be realistic. How can we generate realistic and useful compositions? Thank you.